All right, hello everyone. We are going to solve this problem that has to do with a piece of wood that is sitting in some water, and 90% of the wood is below the surface of the water, something like that. And then there's a rock sitting on it. It's kind of a weird looking rock, but anyway, got a rock sitting there. And so part of our visualization, we've got a sketch here. We can also draw a free body diagram for the wood. All right, well, what forces are acting on the wood? There's the weight of the wood, and there is a buoyant force because it's displacing some water. And what else? Well, what else is touching this piece of wood? The rock is, and the rock is pushing down. And so this is the normal force of the rock on the wood. But since it's in equilibrium, that normal force of the rock pushing on the wood is also equal to the weight of the rock. If it were accelerating, then that would be a different story. All right, so we've got a nice free body diagram there. We have specified a coordinate system, and we're going to be trying to find the weight of the rock. We expect that to come out to be a positive value whenever we're using Newton's second law, and we're going to be using Newton's second law. To solve for a force, we're solving for the magnitude of that force. And we expect it to come out to be units of newtons because it is a force. All right, so we're going to use Newton's second law, as I mentioned. We might also need to take advantage of the density equation. And we might need the buoyant force equation. And remember, in the buoyant force equation, it's the fluid's density and the volume of fluid displaced that are important. All right, and so we can go ahead and sum the forces. So we have FB in the positive direction minus the weight of the wood minus the weight of the rock equals 0, because the acceleration in the vertical direction is 0. And we say, okay, well, we're trying to find the weight of the rock, but we don't know the buoyant force and we don't know the weight of the wood yet. So we're going to have to find a lot of things in this equation. Well, to find the weight of the wood, well, if we knew the mass of the wood, we would be able to find the weight of the wood. So let's use this equation, apply to the wood. All right, so the density of wood equals the mass of wood over the volume of wood. So 500 kilograms per cubic meter equals mass of wood divided by 0.12 meters cubed. So the mass of wood is going to be 500 times 0.12, which is 60 kilograms. So the weight of wood is going to be 60 kilograms times 9.8 meters per second squared. So it should be roughly 600. And it turns out it's 588 newtons. All right, so we got that squared away. Now we need to figure out the buoyant force. And I'm going to put this up in the plan section, even though it's really part of executing the plan. The buoyant force. As for the density here, we do need to keep this straight. It's the density of the fluid, and it's in water. So that's 1,000 kilograms per cubic meter times 9.8 meters per second squared. Remember, G is a scalar. And then the volume is going to be 0.9 times 0.12 cubic meters. Okay, because only 90% of the wood is below the water level. So only 90% of the piece of wood is submerged, and only 90% of it is displacing any water. And so now we can calculate this out. 1,000 times 9.8 times 0.9 times 0.12. And we get 1,058.4 newtons. All right, so now we can fill these values in. 1,058.4 newtons minus 588 newtons minus the weight of the rock equals 0. So now we can solve. We get 470.4 newtons, but I'll just round it to 470. I'm adding W rock to both sides, and we have our answer. All right, so is the solution complete? Look back at the question. They only asked us one thing, so yes, the solution's complete. Is the sign of the answer correct? And we look here, we have a large number minus a smaller number, so we get a positive number. Here we have a negative sign. We add W rock to both sides. It came out positive. We expected it to be positive anytime we're using Newton's second law. We're finding magnitude, so the sign is correct. The units, well, we had newtons minus newtons, so that was easy. Here we had more complicated units. We had kilograms per cubic meter times meter per second squared, and then times meter cubed. And so we have to look more carefully here. So meters cubed and meters cubes cancel, and then we have kilogram meter per second squared. So that is a Newton. And over here, we had kilogram per cubic meter times cubic meter. So that gave us units of kilograms for the mass. And then we multiplied by meter per second squared. And that again was a Newton. So the units are correct. Is the magnitude of the answer reasonable? Well, it's kind of hard to say, but it's certainly good that the weight of the rock is smaller than the buoyant force. That makes sense. And we can go back and check. We can add these two together, and they do add up to that. So as far as we can tell, the magnitude is reasonable. All right, that's all there is to that problem. So we got to use 3 different equations from this unit as well. Well, two equations from this unit and 1 from a prior unit. We have to practice our free body diagram drawing skills. And there you have it.